add to it lecture 14. Okay, so we talked about the response last time for underdamped and overdamped and critically damped, which means that for each response there is a the equation for the response is different for each system. I mean, for zeta less than 1, zeta equal to 1, or zeta greater than 1, we have to use the corresponding equations, which are summarized in the formula sheet. You will see in the formula sheet that there is a equation for underdamped, for overdamped, critically damped. Okay, and we solved this example last time, and we talked about the logarithmic decrement. Okay, the logarithmic decrement is a way to measure the damping in a system, which involves an experimental part, like delta equal to ln. This is the definition, that delta equal to ln x1 over x2. So if you have a wave, yes, yes. Okay, so if you have a measured vibration wave, so you can take x1 and x2 are the amplitude of two consecutive or successive amplitudes. So it has to be, the two amplitude have to be separated by a period of oscillation. Okay, and then you use this value, delta equal to ln x1 over x2, with the derivation we obtained for delta equal to 2 pi zeta over square root of 1 minus zeta square. You can find zeta from here. If zeta is large, yani large, relatively large, then you can use, of course, this should be less than 1. Okay, so as you can see, the graph is up to 1. So if it is, this is all derived for zeta less than 1. If zeta is small, very small, less than, as you can see from the graph, this is, you have two equations. This is the exact equation, and this is the approximate equation for delta, and are represented by this graph. This is the exact equation, and this is the approximated equation, and they are in good agreement, as you can see from the graph, in the range for zeta less than maybe 0.3 or 0.2 in this region. So if zeta is small, then you can use this equation to make the equations simpler, or the analysis simpler. So if you have, usually in machines, the zeta is very small, 0.05, 0.1. So you can assume 2 pi zeta. Okay, so we have two examples about the logarithmic decrement. The following data are given for a vibrating system with viscous damping. The weight equal to 10 pounds, K equal to 30 pounds per inch, and C is 0.12 pound per inch per second. Determine the logarithmic decrement and the ratio of any two successive amplitudes. So here we have all the parameters are known, the weight, the stiffness, and also the damping. So you can calculate nature frequency, damped frequency if this is under damped. So the first thing we have to see zeta. How much is zeta? We cannot proceed to omega d before we find zeta, because if zeta is greater than 1, yes.
ما تبين عندنا الشاشة.
Okay, just hold on. Okay, now I did the sharing screen. Huh?
Okay.
So the first thing you have to find is zeta in order to proceed. Nature frequency, this is a spring mass temper system. There is no need for derivation for the equation of motion and reach to the expression of omega n. Omega n is directly square root of k bar. Okay, and we have the mass is not given, is the weight is given using the pound. So it is k over m, and M is W over G, so it is 30 divided by 10 divided by G. G is in inch per second square, 386 or 38614. Okay, so that is G, 386 inch per second square. And omega n becomes 34. Cc is from the definition 2m omega n. This is 2 times 10 over 386 times 34 equal to 1.76 pound per inch per second. And zeta is C is 0.12, so we get underdamped system. Okay, so this is less than 1 and this is underdamped case. Okay, and then we can answer the question. The question is determine the logarithmic decrement, and this will be true if zeta is less than 1. Otherwise, there is no logarithmic decrement. There is no reduction in, there is no cycles, no oscillations. Then the ratio of any two successive amplitude, now we can proceed. After we found zeta, we can substitute here 2 pi zeta over square root of 1 minus zeta squared. We get 0.429. I think with the zeta 0.0681, you can use delta equal to 2 pi zeta as well, because this will be small. 2 pi times 0.0681, which will be almost similar. Okay, this is 0.4278. So to 3 decimal places is 428. So you can see the error is in the 3rd decimal place. Okay, and this is delta, which is required in the question. The amplitude ratio of any two consecutive cycles or successive cycles, they mean the same thing. Eh? So two amplitudes separated by tau d. Okay, from the same definition of delta, then delta equal to ln x1 over x2. So you can put x1 over x2 on one side, which is equal to e to power delta. x1 over x2 equal e to power delta. Delta is 0.429. This becomes 1.4. This is the ratio, meter by meter or centimeter by centimeter. Now this is the end of the example, but you know the meaning of this. This means x1 over x2 is the same as x2 over x3, because there is no time here. As far as x1 and x2 or two consecutive cycles amplitude, then this will be the same. So for underdamped, okay, suppose I have this is x1 and this is x2 and this is x3 and so on. This will not be 0. Ideally, this will not stop. Okay, it will be forever, but this is ideal. Okay, so x1, it means that x1 over x2 is equal to x2 over x3. So any two amplitudes of consecutive cycles, the ratio is the same. So this is the ratio of any two amplitude of two consecutive cycles is constant. So this value is constant, and this is the characteristics of underdamped case, that there is that the ratio is constant. Okay, example 13 show that the logarithmic decrement is also given by the equation delta equal to 1 over n ln x0 over xn, where xn represents the amplitude after n cycles have elapsed. Okay, this is part of the question. The second part, plot a curve giving the number of cycles elapsed against zeta for the amplitude to diminish by 50%. The original equation was delta equal to ln x1 over x2. Okay, here the question is to prove, and the x1 and x2 are amplitude of successive cycles. Here x0 and xn are separated by number of cycles, n cycles. Now x0 means, I will just use you can say this is x0 and this is x1 and this is x2 and so on. X0 is the amplitude of the first cycle. This is the first cycle. And x1 is the amplitude of the second cycle. X2 is the amplitude of the third cycle. Okay, so x0 and x1, they are separated by one cycle, n equal to 1 here, between x0 and x1. If you want to relate x0 and x2, it means n equal to 2. Okay, so x0 is the beginning of each, that amplitude is the beginning of each cycle. The amplitude of a given cycle. Okay, that is the amplitude, because a cycle is from here to here. This is a cycle. What is its amplitude? Is the first value at the beginning of the cycle, that is the amplitude. Okay, so we want to prove that this is true. Okay, since the amplitude ratio is constant, we can say that x0 over x1 is equal to x1 over x2, equal to x2 over x3, up to xn minus 1 over xn. Each value is e to power delta. Okay, because you can put here x1 over x2 equal to e to power delta, as well as x2 over x3. So each term here equal to e to power delta. We can use chain rule, x0 over xn equal to x0 over x1 multiplied by x1 by x2 up to xn minus 1 over xn, so that this will end up only x0 over xn, because x1 and x1 cancel out, x2 and x2 cancel out, xn minus 1 with xn minus 1 will cancel out. So you will have only x0 over xn. This is the chain rule, right? And each term is e to power delta. So here is e to power delta, this is e to power delta, this is e to power delta, and so on, and this is e to power delta. So this is e to power delta multiplied by itself n times. So it is e to power delta to power n. And then this becomes e to power n delta. You take ln both sides of this equation. Now we reduce this to x0 over xn equal to e to power n delta. And then you take ln both sides, you will get that ln of x0 over xn equal to ln of e to power n delta. And you use the properties of the logarithm. This will be n delta multiplied by ln, and ln of e is 1. So this will be n delta. And you put delta on one side, becomes this equation. Delta equal to 1 over n ln x0 over xn. It means you can relate any amplitude, any two amplitudes separated by number of cycles. For n equal to 1, this will reduce to the usual equation. For n equal to 1, delta will equal to ln x0 over xn over x1, which is the first cycle. Or even x1 over x2. Okay, any two successive cycles that is n equal to. Now the second part of the question, not here. Second part of the question is okay, so we proved that delta equal to 1 over n then x0 over xn. Plot a curve giving the number of cycles elapsed which is n, against zeta for the amplitude to diminish by 50%. So the required is a plot of n versus zeta. This is required for x0 for xn to be equal to 50% of x0. That is the question. To reduce by 50% or to 50%, here is the same, right? By 50% to 50%, this is 50%. But sometimes the question says find that diminishes to or diminishes by 20%. By. So how much it is? It is 80% of x0. But if it says reduces to 20%, it is 0.2 times x0. Okay, so 50% mean this is 0.5 x0. Okay, so we have that delta equal to ln x0 equal to 1 over n. We will use the equation we proved. Okay, this is 1 over n ln x0 over xn is 2 because x0 is x0 and xn is 0.5 x0. That is given to reduce to 50% or by 50%. So x0 and x0 cancel out. We get ln of 2 because ln of 1 over 0.5 is ln 2. Okay, delta also equal to, for approximation, is 2 pi zeta. So we can equate the two equations. 2 pi zeta equal to 1 over n ln 2. Okay, the question is to plot n versus zeta. So you put n on one side and zeta on the other side. So this will be ln 2 divided by 2 pi multiplied by 1 over zeta. Okay, so ln 2 over 2 pi is, I think, 0.11. Okay, 0.11. Okay, so this is the equation of the, and the plot, of course, is that when zeta equal to 0, which is undamped, how many cycles required to reduce to 50%? Infinity, which is makes sense that this is not valid, right? So this will be no reduction. So the plot will be n versus zeta will come from infinity and become asymptotic to zeta. If zeta is very large, infinity, this will be 0. Okay, so let me print this page. So you see the numbers at least. Okay, so this is the continuation. Okay, so this is the continuation of the example. So we get that in zeta, this is equal sign here, is 0.11. And the graph shows n number of cycles of for 50% reduction in amplitude versus the damping factor or damping ratio, zeta. So as you can see, it's coming from infinity and become asymptotic with zeta. And there are some numbers you can pick from the graph that it will require, let's say, 5 cycles when it is when the zeta is 0.025. I'm guessing here in the middle. Okay. And it will take, let's say, about 2 cycles if zeta is just above 0.05, maybe 0.06. Okay, so it is this is the graph required. Okay, there is one more topic in this chapter, which is the column damping. I will postpone this to next week, and I will not put this one in the exam, in the test, so that this is a new topic. And we will solve the tutorial now. This is the last tutorial in this chapter, tutorial 5. Yes, most of the question of this tutorial is about viscously damped system, except maybe the last question is about the last topic. Okay, so this is the tutorial 5 and the last tutorial in chapter 2. It's about damp-free vibration, and the damping is 2-part. So from question 1 to question 7. I don't know, there is 8 here. Oh, this is 8. Okay, and do we have one more? No. The last question is about column damping that we will postpone this to next week, and it is not part of the test one. So this one will include up to question 7 only. Okay, a mass of 0.907 kilogram is attached to the end of a spring with a stiffness of 7 newtons per centimeter. Determine the critical damping coefficient. We have the formula sheet. You can use it. I will put this part of the attachment of the test. Okay, just to have an idea. Okay, the formula is 2 parts. Free vibration, and then we have force vibration. Force vibration is chapter 3 and chapter 4. So what you need from the tutorial is only this page number 1. Okay, so the question, the tutorial has also harmonic motion that we need from chapter 1. Okay, so the question is, determine the critical damping coefficient, CC, which is here. Equation, in case you okay, this one, CC equal to 2M squared of K over M. And for the spring mass system, directly use this equation for spring mass damper system. Okay, here is no need to mention a damper because the question is to find the critical damping coefficient, and it is function of K and M. It is characteristic of a system. Okay, the mass is given. Only the thing you have to do is convert the stiffness to Newton per meter to use base units. Question 2, a mass suspended. Okay, so you can use C equal to, or CC equal to 2m square root of K over M, or equal to 2 square root of Km, or equal to 2m omega n. Anyone. Question 2, a mass suspended from a spring is subjected to damping proportional to velocity. Which one is that? This is the viscous damping. You take m inside the square root, becomes m squared. داخل الجذر بصير m تربيع لا في المقام في البسط مع الام اللي تحت بتروح له مو قادر تركز شكلك. هذه 2m هاي this is the equation 2m square root of k over m. You take m inside. Okay. The frequency of damped vibration. Okay, so here question 2. The system is a spring mass and damper, and the properties of the damper is viscous. That is the what we mentioned about viscous damper, that the force is directly proportional with velocity, and it is mentioning the properties. The frequency of damped vibration is 1.5. So this is tau d, right? 1. Fd in hertz. And the amplitude decreases to 20% of its initial value in one complete cycle, n equal to 1. In one complete cycle mean n equal to 1. And it reduces or it decreases to 20%. Determine the frequency of free and damped vibrations of the system. The frequency of a free and damped, which means Fn. Okay, so we start with the logarithmic decrement. Delta equal to ln x0 over x1 or x1 over x2. And this is equal to ln of x0 over 0.2 x0 reduces to 20%. So it is 0.2. And 1 over 0.2 is ln 5. And also equal to 2 pi zeta divided by the square root of 1 minus zeta squared. Now, ln 5, if this is less than 2, how much? So you can take the approximate if you want to make it easier. This is 2 pi zeta. And you can find zeta from here. Since it is less than 2, you can take the approximate. Okay, so you will find zeta within 2 decimal places. 0.25. 0.25? 0.256. So we have to make this 6. To take 2 decimal places. So this is zeta, but the question is to find Fn. We know that omega d equal to omega n square root of 1 minus zeta squared. And also, when you substitute for omega d, it is 2 pi fd equal to 2 pi fn square root of 1 minus zeta squared. That 2 pi and 2 pi cancel, and then you can get fn from here. Okay. 1.55. Okay, that the same as the answer. Yeah.
نقدر نختصر هاي شو اسمه القانون انه بس اعتبرنا نزله صغيره وقلنا بس شلون عرفت نزله صغيره؟
Okay. Yeah, from ln of 5. Ln of 5 is 1.6, which is less than 2, and as you can see from the figure that this figure. Yeah, from this figure, if this is less than 2, you can take the approximate. Okay, question 3. A vibrating system consisting of a mass of 2.26 kilogram and a spring of a stiffness 17.5 Newton per centimeter is viscously damped such that the ratio of any two consecutive amplitude is 1 and 0.98. Any two consecutive amplitudes. The first one is 1, the second one is 0.98. So we have x1 and x2 given. Determine the natural frequency of damped system. The natural frequency of undamped is directly obtained from the square root of k and m. And in order to find the natural frequency of damped, I need to find zeta. So I need to work on delta first, equal to ln x0 over x1, which is given. And to compare this value of less than 2, you can use 2 pi zeta. Otherwise, you use the exact solution. Okay, and then you find zeta, then you can find fd equal to fn square root of 1 minus zeta squared. And you find fd. This is required. Fd or omega d. It didn't say, it didn't mention that what is the unit required. So an answer are not given. So you can use, you can find Fn or omega, I mean omega d or omega n, omega d or Fd. It's up to you. Since there is no, not specific in the question, you can find omega d or Fd. The logarithmic decrement, which we should find first, delta, the damping factor or the damping ratio. Sometimes we call it damping ratio, which is zeta. The damping coefficient, which one is the damping coefficient? C. Good. And this is obtained from the definition of zeta, that it is C over Cc. So once you find Cc, you can find zeta, C. Question number 4. A vibrating system consists of 4.534 kilogram, a spring of stiffness 35 Newton per centimeter, a dashpot with damping coefficient 0.1243 Newton per centimeter per second. The dashpot is the viscous damper. Find the damping factor, zeta, the logarithmic decrement, delta, and the ratio of any two consecutive amplitude. The system is same as the one we discussed in the lecture, spring, mass, and damper. So there is no need for derivation. All the equations are in the formula sheet, just the direct substitution. Straightforward. Okay, question number 5. Set up the differential equation of motion for the system shown below. Determine the expression for the expression for CC. ما يسمعوني المفروض. Okay. So we are back. The natural frequency of damped oscillation. The natural frequency of damped oscillation, which is Fd or omega d. Now the system here is, you cannot use, the first equation, the critical damping coefficient Cc, you cannot use Cc equal to 2m omega n here, or equal to 2 square root of k over km. Okay, or the other one. You cannot use this directly because the system is not a spring mass system. It is a rigid body, a rigid bar. You have to find the equation of motion first. And the equation of motion, you compare it with the standard one. So this, we cannot use this directly. We have to get the equation of motion and put it as theta double dot, okay, in the as J theta double dot plus C in the torsional CT, okay. I'll just call it T for torsion or rotation, and theta dot plus KT theta equal to 0 for free vibration, and compare this, and this is obtained from Newton's second law. In sum of moment about a pivot point equal to J theta double dot. If you call this is point O, then you need to use sum of moment about O equal to J O theta double dot. And then you compare with theta double dot after we divide by J O with theta double dot plus 2 zeta omega n theta dot plus omega n square theta equal to 0. You have to compare with this. Do not use those equations directly. You have to use this equation. So what is the expression for omega n? Is the coefficient of theta is omega n square, and you can obtain zeta from here, and then use the definition of zeta equal to 1. It means that this value will give you critical damping coefficient. Okay, so I have time, so I can solve this with you to see the procedure. But this is the procedure for any problem, like question number 6, as well as number 7. Those are 3 questions here. Need, first of all, the equation of motion. We cannot use the equations in the formula sheet. Where is the formula? Okay, we cannot use the formula sheet directly here. Where is it? Okay, like omega n equals square root of k over m. There is rigid body and there is distance. Okay, and we cannot use omega n equal to square root of kt over j. Where is the other equations? Okay, as we did in tutorial number 3. Tutorial number 3, we did the same thing. Okay, so when the problem is rigid body in rotation, will require to find the equation of motion. If it is a mass in a translation with arrangement of springs or pulleys, then we can get the equivalent directly, the K effective or K equivalent, without derivation of differential equation. But if it is something like those systems, you need to get the equation of motion. Okay, so now we will see. Hopefully, this will be clear when we solve this together. On the same, this is a pivot point, as you can see. So it only carries OX and OY. And the equilibrium position, we don't put the weight, as you know, because for equilibrium, this will have K delta, and this will have mg. They will cancel each other. Or you can think of this as you are looking from the top of you. This is vibrating horizontally. Okay, so the weight, you don't put the weight. If you put the weight, you have to put K delta. So they will cancel each other. So the free body diagram will be, if you take theta clockwise positive, then the rigid body arbitrary position will be in this direction. And then the spring force, the spring is under tension, its force is upward, and it's equal to K times, this is A, and this is theta. You can put everything in terms of theta. This will be K times A sine theta. And you can do the approximation directly, which is Ka theta. The damper will be under compression and it is pushing the bar upward. So the force is upward. And the force is C times the velocity at this point, which is you take the derivative of A sine theta. Okay. And with the approximation, it will be A theta dot. No other forces to be added on the free body diagram. Because even if you put OX and OY, you will take moment about O and will cancel. One more thing we have to be careful about. What is JO here? because we will use the sum of moment equal to Jo theta double dot. We need to know this bar is massless or it has a mass. Okay, set up the differential equation of motion for the system shown below. Determine the expression. Okay, so it is not mentioning anything about the mass of the bar. So it will take it as a rigid body. We cannot assume flexible because this will take us out, beyond the scope of the course. If it is flexible, then it's something else. Pivoted and flexible, it means partial differential equation. So we take it pivoted and rigid body. And since the mass is not mentioned here, we take that J of the bar is 0. Then Jo is only of the bulb mass, which is point mass here. Okay, not a rigid body, this is a bulb mass. If it is a disk, then we have to see if this is locked or unlocked. Okay, but this is a bulb mass. Then we take the sum of moments. I will put the equation of motion here so that I don't go away or far away from the free body diagram. Sum of moment about O equal to Jo theta double dot. Okay, the theta is clockwise positive. The moment of the two forces are counterclockwise, so they are negative. And what is the definition of moment? Force times distance, perpendicular distance. But in the test, always they put forces. I don't know why. For so many semesters, when they write this equation, but they put the forces as if they something new for them. This is Ka times Ka theta times A again. So it is Ka squared theta minus C times A squared times theta dot equal to Jo theta double dot. Okay, so this equation becomes, you put everything on one side, Jo theta double dot plus Ca squared theta dot plus Ka squared theta equal to 0. So this is our differential equation. We put in Jo first, okay, is equal to JCG, which is 0, plus M times the distance squared, L here. Okay, the location of the mass from pivot. It is L, D, whatever it is given. We use that. So it is M times L square, and this is 0 because this is bulb mass. Its JCG is 0. Okay, if it is a disk, as we did in the tutorial 3, if this is a disk, we have to know whether this is locked or unlocked to the R. It's a bulb mass. If it is unlocked, it is a bulb mass. Okay, so this equation will be ml squared theta double dot plus Ca squared theta dot plus A squared theta equal to 0. There is K here, right? K. Now we divide by ml squared. This will be theta double dot plus C over M A over L squared theta dot plus K over M A over L squared. So from here, what is omega n? Yeah, the coefficient of theta. So omega n is square root of K over M A over L squared, which we can take L A over A outside, L A over L square root of K over M. So as you can see, it is not square root of K over M only. This is obtained from the by comparing with the standard. And also 2 zeta omega n is the coefficient of theta dot, which is C over M times A over L squared. The question is, what is the critical damping coefficient? We have a damper C here. What is the value of C that makes the system critical? Okay, critical means zeta equal to 1. So what you do here, put zeta equal to 1 Therefore, C becomes CC. Okay, so when you put zeta equal to 1, this will be 2 times 1 times omega n equal to CC over M A over L squared. And you can find CC from here. Omega n is, so this will be 2 times A over L square root of K over M equal to CC over M A over L squared. And you can get CC on this side as multiplied by M and multiplied by N squared, and this becomes 2 L over A square root of Km. Okay, I think there is a mistake here. This is over A. And the other thing is to find the damped frequency, the damped natural frequency, the natural frequency of damped oscillation. So it is not omega n, it is asking for omega d. Omega d is by from this equation, omega n square root of 1 minus zeta squared. Omega n is A over L square root of K over M square root of 1 minus zeta squared. Zeta, again, we go back to this equation to find zeta. Okay, do not use C over CC here because you need to get C equivalent, not C of the damper. You need to get C equivalent. So to be safe, you use this equation to find zeta. So this will be 1 minus, and zeta is C over 2M omega n A over L squared. تغير اللون. This is all squared. And you need to replace omega n in terms of the given parameters. So this will reduce to A over L square root of K over M 1 minus CA over 2L square root of KM all squared. This is the final equation. The question number 7, I'm not going to solve it because it is similar to question 5, except that we have here rigid body with a mass M. There is no Bob mass, that the rigid body has a mass equal to M. Then you will do the same thing. You will use the same equation, sum of moment about O equal to JO theta double that. But JO is the moment of inertia of the bar about point O. Okay, which is 1 over 3 given 1 over 3 ml squared. If JCG is given, you use parallax theorem to find JO. You draw the free body diagram, take the moment of the forces. Okay, let's say we take, this is the equilibrium, and this is the arbitrary position. Then this will be under tension, its force is upward, and this force is upward, and you can use the approximation that this is K times A theta, and this is C times L theta dot velocity. And those are forces. You take moment about O, will give you the moments. Multiply by distance will give you the moment. Question number 7. Question number 7, this is a cylinder rolling on a horizontal surface without slipping. It is restrained by spring and damper as well. So you cannot use conservation of energy because this is non-conservative system because of the damper. So you don't use T plus U equal to constant or D by dt of T plus U equal to 0. Not valid here because the system is not conservative. Okay, so what you need to use, one of the things that we learned is using Newton's second law. And this is similar to question in the tutorial number 3, but you have a damper. And I think in tutorial 3, I put the 2 methods, tutorial 3, yes. Yeah, this one. So we talked about energy method in tutorial 3 because this is conservative system. And also I gave you an alternative method is by taking moment or sum of forces. But here you need to use this method, the Newton-second law. Don't forget to put the friction force because there is no slipping and the friction force is not known. It is unknown. You use F is the unknown force. You don't substitute for Fk or Fs. And then instead of having only Kx, we have Kx and Cx dot. That's it. So you will add to this the viscous, the force of the viscous damper. And then you will do the same thing, similar. Okay, the complete solution is not here, but I think I did it maybe in section 2. Yeah, so I can just copy this. You can see it. From section 1. Okay, so this is the end of this lecture. Yeah. Okay. In tutorial number 5.
السؤال اللي قبله السؤال السادس ممكن نشتغل على البعض نشتغل من رأي المثل من رأي المثل بدنا نحسب الافكتيف ماس.
اوكي.
لا انا اسال يعني
لا ما له علاقه بالرالي ميثود. Rayleigh method is used for either discrete mass system or distributed mass parameter system, which are flexible. This is pivoted. So you neglect the relative deflection that occurs in the bar. This is rigid. Yeah, this is not Rayleigh method. No.
شنو يقصد the ratio of any two negative amplitudes is 1 and 0.98. نص غلط صراحة.
لا مو غلط.
مكتوب the ratio. المفروض ما يكتب the ratio. The value of the amplitudes. يقصد value.
يقصد الvalues. But because it is 1, he assumed this is ratio. It is 1. Yeah, and this value might be not the actual value. So if you divide by x0, you make it a ratio. No, this is the one ratio, but instead of giving you, let's say, 2 centimeter and 2 centimeter and 1.5 centimeter, you divide by 2 both the values. You divide by x0. So you get the amplitudes given as ratio. Okay, but this is a good point. Valid. Okay, good luck. We'll see you next time.